In this lesson, we're going to take a look at the precise epsilon-delta limit definition. So in this lesson, we're going to take our intuitive limit definition, which we have stated right here, and we're going to make it mathematically precise. You see, this definition, as we have it stated, isn't really precise enough for us to actually prove that the limit of a particular function is equal to some number L, nor is it precise enough to actually prove theorems that we're going to need later on related to limits. So we need to make this mathematically precise, and here's how we're going to do it. So let's quickly recall what the limit definition states, the intuitive limit definition. It says that if there's a number L such that the function f of x gets closer and closer to that single number L as x is taken closer and closer to the number c without actually taking on the value of c, then we say the limit of f of x as x approaches c is equal to L. So in other words, as x is taken closer and closer to c, f of x gets closer and closer to the number L. Well, this terminology gets closer and closer just isn't mathematically precise, so that's what we're going to have to work on. So here's what we're going to do. To make the statement f of x gets closer and closer to the single number L precise, we're going to replace it with this statement. The absolute value of f of x minus L is less than epsilon for some arbitrarily small number epsilon that's positive, greater than 0, as small as we would like to make it, as long as it stays positive. Now, take note that this is equivalent to saying that f of x is between L minus epsilon and L plus epsilon. And that's because this inequality with the absolute value here is equivalent to saying f of x minus L is between negative epsilon and positive epsilon. And then if we add L to both sides, to all three parts here, if we add L to the left, the middle, and the right term, then we would get this right here. So keep in mind that this inequality with the absolute value here is equivalent to saying f of x is between L minus epsilon and L plus epsilon. So that's what we replace the term f of x getting closer and closer to the single number L with. Now, we also have to replace the statement as x is taken closer and closer to the number c. We replace that with this statement. The absolute value of x minus c is less than delta for some small number delta greater than 0, and also positive, that it has to be greater than 0. Now take note that this statement, that the absolute value of x minus c is less than delta and greater than 0, is equivalent to saying that x is between c minus delta and c plus delta, and that x does not equal c. The does not equal c part, that comes from this piece right here, the greater than 0. Saying that x minus c in absolute values greater than 0 means that x cannot equal c. And keep in mind that the reason we don't want x to equal c is because when we're talking about the limit as x approaches c, recall that we don't want x to ever actually take on the value of c. So that's why we don't want x to equal c. So we want x to never equal c. Now also note that the x is greater than c minus delta, less than c plus delta. Once again, that comes from the absolute value statement by taking this and just rewriting it as and then we add c to each term, and we obtain this over here. So that's where that's coming from. So it's coming from this piece right here. All right, now, so let's take a look now at our precise epsilon-delta limit definition. So here it is. So here's our new definition. So we say that the limit as x approaches c of f of x equals L, provided that for every epsilon greater than 0, any number given to you that's greater than 0, there exists a number delta greater than 0, such that f of x minus L in absolute value is less than epsilon whenever x minus c in absolute value is less than delta and greater than 0. That's our definition. Now we'll take a look at some examples graphically to illustrate what is going on here. It looks a little intimidating with all these symbols, but we'll make sense of it. Now let's note one other thing. In this definition, you need to think of the epsilon as being a number that's given to you, a small number given to you. So if you're given that number, then you need to prove that you can find a number delta, which normally will be some function of epsilon. You know, it might be like epsilon divided by 3 or some function of epsilon. So normally the delta is a function of epsilon, in which f of x minus L is less than epsilon whenever x minus c is less than the delta and also greater than 0. Now, as we'll see later on when we do our problems, for the simple problems that we're going to look at, this part right here normally never comes into play. We'll see that as we work through some problems, but it is still necessary to state this. But for our problems that we're going to be doing, we're not going to need to worry about this piece right here. All right, now let's take a look at some graphical examples illustrating what is going on here with this definition. So here, let's illustrate graphically why the limit as x approaches 2 of x squared is equal to 4. We want to illustrate why that satisfies our new precise epsilon-delta limit definition. Well, down here we have the graph of y equals x squared. It's this blue curve right here. Notice we have 2 on the x-axis here. If we go up and over, right there is 4 on the y-axis. So we want to prove that as x is taken closer to 2, the f of x values, which are right here on the y-axis, get closer to 4. All right, so why is our epsilon-delta limit definition satisfied? Well, think of the epsilon greater than 0 as being given to you. So you're given some small number epsilon, and you form this little epsilon neighborhood around 4. So you see there's 4 minus epsilon and 4 plus epsilon. It does look like there is a neighborhood around 2, a region around 2 right here, where as long as I pick x within delta units of the number 2, f of x will stay within this band over here. It will stay between 4 minus epsilon and 4 plus epsilon. Remember, that's what we want. We want the f of x to stay between L plus epsilon and L minus epsilon. In this case, the L is 4. Well, notice from this graphic here, if I move the x within that delta neighborhood around 2, the red dot on the y-axis always stays between 4 minus epsilon and 4 plus epsilon. So it does look like there is a delta neighborhood around 2 in which this over here, f of x, remains between 4 minus epsilon and 4 plus epsilon. Now that has to be true for every epsilon. So suppose that you made the epsilon smaller. Well, so suppose we did this. Suppose you make the epsilon smaller. So there, we're going to make it smaller now. Well, notice we made it a little smaller now. Notice we can still find a little delta neighborhood around 2 in which, as long as we pick x in here, f of x will stay between 4 minus epsilon and 4 plus epsilon. So just notice that as I move x in there, how the f of x's stay between 4 minus epsilon and 4 plus epsilon. And we can see graphically that that's going to be true. There's always going to be a delta neighborhood around 2, no matter how small I make that epsilon. No matter how small it becomes, there's always going to be that neighborhood around 2. So that's graphically why the epsilon-delta limit definition is satisfied. And we will take a look at some examples where we work with that definition more precisely in a few minutes. Now let's notice one thing here from this graph. It doesn't look like the delta here, right, there's 2 plus delta, is really the same as the delta over here. In other words, it looks like this delta is a little bigger than this one over here. And that's because this is a quadratic curve. But don't worry about that right now. As long as there is some delta neighborhood around 2, actually if this is a 2 plus delta here, right here would actually be 2 minus delta. But still, as long as x is taken in here, f of x will be within the 4 minus epsilon to 4 plus epsilon band. So yes, the distances here don't look exactly the same, but that's not an issue. And we'll clarify that as we look at some examples in a second. Now let's take a look at a problem where the epsilon-delta limit definition is not satisfied. So let's consider this function. This is a piecewise defined function right here. And down here we have its graph. So the blue curve is its graph. Notice that at 1 we have a break in its graph. And notice that as we approach 1 from the right, it looks like our function values are approaching that number right there on the y-axis, and that would be the number 3. I don't have it labeled here, but it would be 3. So it looks like our right-hand limit as we approach 1 from the right is 3, and as we approach 1 from the left, it looks like our function values are approaching 2. So it looks like our full limit does not exist because our left and right hand limits are different numbers. We're not approaching a single number. So let's see why the epsilon-delta limit definition would fail in this case. Well, let's suppose that we tried to force the limit to be 2. Suppose we made the statement that the limit as x approaches 2 of this function, as x approaches 1 of this function is 2. Well, let's see why the epsilon-delta limit definition would fail. Well, notice that on our graph down here, we currently have 2 minus epsilon right there and 2 plus epsilon right there. So that's for some arbitrary number epsilon that's given. Now let's see what happens as we make epsilon small. Well, if we make epsilon a little smaller than what we have in the picture currently, notice what happens to the dotted lines. All right, let's stop right about here. Notice that this dotted line here, at 2 plus epsilon, it never hits the graph anywhere. And that 2 minus epsilon, it does hit the graph, and then we can drop down to that point right there. Right there would be perhaps a 1 minus delta. However, if we look now, we see that there is no delta neighborhood around 1 in which if I place x in here, f of x stays in here. It doesn't happen because you see, we can let x get all the way as close to 1 as we want, but our function values up here will always stay outside this epsilon band. You see, just watch this, as I let x get closer and closer to 1 from the right side, I can never force the red dot to be between 2 minus epsilon and 2 plus epsilon. It just doesn't happen. I can't force it down in there. So therefore there is no delta neighborhood around 1 in which f of x is between 2 minus epsilon and 2 plus epsilon. Or in other words, there is no delta in which the absolute value of f of x minus 2 is less than epsilon for every x in the delta neighborhood around 1. This just does not happen. Alright, so that illustrates how the epsilon-delta definition can fail, and that's good that it failed in this case because we wanted it to fail. So this illustrates why we use that epsilon-delta definition, because it works when we want it to work, and this example illustrates how it can fail when we want it to fail. We don't want it to work in this case. Now let's take a look at actually working some problems with this epsilon-delta limit definition. So here we want to use the epsilon-delta limit definition to precisely prove that the limit as x approaches 2 of 2x plus 1 is equal to 5. So here's what we want to do. We assume that epsilon greater than 0 is given to us. It's some small number. We want to find a delta, and it will be a function of epsilon, positive delta, such that f of x minus L is less than epsilon whenever x minus c is taken to be taken less than delta. And it's also going to be greater than 0, but like I said, this piece right here we're not going to have to worry about. We mostly have to worry about that part right there. Alright, so let's do this. So we're going to start out with this statement here, and we're going to mathematically manipulate it to figure out how close does x have to be taken to c. Now in this case, our f of x is 2x plus 1, our L is 5, and our c is 2. So keep that in mind. So we'll start out with this. Now that's equivalent to stating that is the same as, that means is the same as. Now we're going to put in what our function is and what our limit L is. And now let's manipulate this and see if we can extract we want to end up with an x minus 2 from here somehow. And then whatever is left over on the right hand side, that's going to be our delta. So let's manipulate this a little bit. So now this is equivalent to, notice I can write this as and now this is equivalent to, I can factor a 2 out. Now we can divide this 2 to the other side, and this is the same as saying and there we go. So you see what we have sitting right here is x minus c. That number 2 right there, that is our c value right there. And so that's what we wanted to end up with. You see right there's our c value that we found is 2. And the delta here is this quantity right here. So the way we read this is we see that as long as we pick x, if you're given, let me restate that, if you're given any number epsilon greater than 0, if you pick x to be within epsilon over 2 units of the number 2, then this statement will be true, and so this will be true. We can work backwards like this. And so this statement right here will be true, And that is the same as saying f of x minus L is less than epsilon. So as long as we pick x to be within epsilon over 2 units of the number 2, then f of x will be within epsilon units of the number L. And we found our delta. So we can just conclude our proof now by writing that if we're given, we can say therefore, that's our symbol for therefore, if we're given any epsilon greater than 0, we would choose the delta to be epsilon divided by 2. And that's our answer. And there we go, we proved it. No matter how small an epsilon you give me, I will be able to find that delta. Now let's graphically take a look at what we've done here and see that this epsilon over 2 makes sense by looking at the graph of 2x plus 1. So here we have the graph. Right here's 2. And right here is our limit L, that's 5. Now you notice that here's currently we have 5 minus epsilon sitting right here, 5 plus epsilon sitting right here. Notice that if we go over and down and over and down, it does appear that there is a delta neighborhood around 2 in which as long as I pick x in that delta neighborhood around 2, notice how the dots on the red values on the y-axis right here, notice how these values stay between 5 minus epsilon and 5 plus epsilon. Alright, so, and no matter how small I make that epsilon, if I make it a little smaller, well, there's still a neighborhood around 2 down here. It just became a little bit smaller. I still have a neighborhood here around 2. Right, there's 2. So that as long as I pick x, in there, the f of x values are staying between 5 minus epsilon and 5 plus epsilon. And we can see graphically that no matter how small I make epsilon, we're always going to have that delta neighborhood around 2. Alright, now notice one other thing. Why did we get epsilon divided by 2? Well, it's because the slope of this line is 2. Notice that if we form a little triangle here, right here, this distance right here is epsilon. The slope of this line equals 2. So if this distance is epsilon, then this distance is going to be half of epsilon. Right? Because epsilon divided by epsilon over 2, well, that's going to be 2, simplifying that fraction. So that's why our delta, this distance, is always going to be epsilon divided by 2, because this is a straight line. And in fact, anytime you're trying to evaluate the limit of a linear function or prove the limit of a linear function, so if you have something like this, the limit as x approaches c of ax plus b. So if you have a linear function, that's just a straight line. If you're given an epsilon greater than 0, your delta is always going to be epsilon divided by the slope of your line a. Well, I should say the absolute value of a. In case this is negative, if this were negative 2, your delta would be epsilon divided by positive 2. That's always going to be the case for linear functions. That's only for linear functions. In fact, we'll see that again in our next example. So let's take a look at this problem. Now I'd recommend that you pause the video here and try this one on your own. try to prove that the limit as x approaches 3 of 4x plus 2 is 14. Notice if you plug the 3 in for x, you do indeed get 14 back. So try this one on your own. So assuming that you've done that, I'm going to go through the answer now. So once again, we assume that epsilon greater than 0 is given. We want to find a delta greater than 0 such that f of x is going to be within epsilon units of the number L, or f will be between L minus epsilon and L plus epsilon, whenever x minus c in absolute value is less than delta. So once again, we'll start out with the f of x minus L less than epsilon, and we will manipulate that to try to extract now in this case we want an x minus 3 in absolute value. So we'll try to manipulate this till we get an x minus 3 less than, and whatever's on the right hand side is what our delta will be. So let's put everything in here. And we'll set that less than epsilon. And now this is the same as saying, now let's see, we'll manipulate this to and now let's factor out a 4. And there now we see our x minus c. The c value is 3 right here. That's our c value right there. And now all we have to do is divide that 4 to the other side. And so this is the same as and there we go. Here's our x minus c, and this value right here would be our delta. So with the way we read this is, if you're given any number epsilon greater than 0, as long as you pick x to be within epsilon divided by 4 units of the number 3, then this will be true, and so this will be true, and so f of x minus L will be less than epsilon. This being your f of x right here, and this being your L right there, the 14. All right. And so then you would say, just to clean things up, you would say, therefore, given epsilon greater than 0, we would choose delta to be epsilon divided by 4. And once again, notice that since this is a linear function, ax plus b, our delta turned out to be epsilon divided by, in this case, our a was 4. And that's what we ended up with. Now, once again, you can just jump right to this. However, it is best if you work through all the details here. You should work through all the details here because this reinforces the concept of how to do an epsilon-delta proof with the limit. So you should go through all of this. You shouldn't just jump right to this answer down here. All right, so that concludes our introduction to the epsilon-delta proofs for linear functions. And in upcoming videos, we'll look at the epsilon-delta proofs for quadratic functions, which are a little bit trickier.